Hey guys, welcome to my YouTube channel. Today we are going to do a simple temperature flow in an annulus. Since the geometry I'm planning to design upon is quite complex, I want to make the geometry in Fluent and then convert it into a foam file and solve it in Fluent. It's an OpenFOAM tutorial for buoyantPimpleFoam, wherein we solve the flow conditions with taking into consideration the temperature. The flow will be an incompressible flow. So yeah, opening space claim here, doing a geometry. Okay, we have our axis. We go to design, sketch mode. Let's pan out. Let's design in the I'm choosing the XY plane here. I'm choosing the XY plane. So yes, we go to plan view. My first I'm modeling the fluid medium here, so it's an annulus. So it is the space in between the two circular pipe structures. So my first diameter, I'll make it as 20, 10 and 20, 20. So we have our pipe structure. Let's end sketch. Let's split these bodies. Click the. So we have split the surface into. So yeah, we have the annular structure. Now let us go back, sketch mode, to the XZ axis. Okay, to the YZ axis. Cool. I'm basically doing 50 mm and then another 50 mm. Then 100 mm, 50 and 50. So yeah, Uh, Now we make a 3-point arc. Same for the other side. So we have our 2D profile and we are going to extrude it along this path line. So the option for that is sweep. Press Ctrl and choose all the lines. Press Enter. Yeah, choose the face. It's done. So this is our fluid medium. This is our inlet. This will be the outlet. And yeah, the outer faces and the inner faces. Okay. Now we move on to meshing. So meshing is really simple. Okay, so before that, let's start with the naming selection. For naming selection, either click on the face and create a name selection. My inlet, my outlet, outer surface, and also my inner surface. Carefully decide it. Yeah, an easy way to choose all the faces are to make a split. Yeah, we make a section plane along the mid one. Okay, and now we choose the faces. So outer surface is done. The inner surface is so if we deselect the inner surface, so inner is selected throughout, outer is selected, the outlet is selected, and the inlet is selected. Okay, and now we mesh. Yeah, ANSYS has given a decent mesh, but we can still make it better. How we do this is by inserting my method. I shall go with multi-zone. I shall have face meshing to make a uniform mesh on either faces. I shall also have, it's not compulsory, it's just to make a better mesh. Number of divisions. I shall choose the faces. Choose the upper and lower edges on both sides. I'm just giving a condition for the number of divisions on along the axis. Okay, this shall be number of divisions. It shall be 40. Generate. So as you can see, we have a uniform mesh over here. We could see the details of this mesh, especially the skewness. The max is 0.1, which is not bad. Orthogonal quality is yeah, which is quite good. This is a quite decent mesh. It's quite coarse on this side. If we want a finer layer of the temperature gradient being formed, we could have more divisions, which how we can do this is increase it to 60. Right. Okay, it's much better. We then proceed. At first, make sure the export option is in ASCII mode. Export this mesh, fluent input file, export in the desired directory. Okay, it has been successful. Now the next step is going into OpenFOAM, converting the mesh to a foam mesh, and then proceeding with the simulation. We'll solve the problem in OpenFOAM. We have the mesh. We should convert it into a foam mesh. So yeah, let's do this quickly. Let's create a folder, work folder first, annulus pipe. It's my work folder. For reference, I'm taking the buoyantPimpleFoam Bernard cells tutorial. It's faster. I want to copy my mesh, paste it, open in tutorial. The command is fluent 3D mesh. D is capital, M is capital, T is also capital, F is also capital. Pipe.mesh. Let's check the mesh in ParaView. It looks good. Yeah, it looks good. I have my my inlet over here, my outlet over here. Inlet velocity is propagating in the z direction, gravity is acting in the negative x direction. You have to keep that in mind. Let's get boundary. Inlet is patch, outer surface, inner surface. Okay. Let's go to, since it's laminar, I do not need any of this. I just need the hydrostatic pressure, temperature, and velocity. Since buoyantPimpleFoam is a buoyancy driven solver, it also requires the hydrostatic pressure. The formula is pressure equal to the hydrostatic pressure plus rho into g into the altitude, the height difference. Since there is no height difference, our P is equal to PRGH, and this is how we shall write it. My velocity, inlet, my outlet, my inner surface, my outer surface. No slip, outlet is zero gradient. What zero gradient does is it doesn't allow any gradient in the velocity to seep through. Fixed value is uniform 0, 0, 0.3, and my internal field is stagnant. Temperature, my internal field is at 300. My inlet incoming velocity is at 298. My outlet is zero gradient. My inlet, inner surface, is hotter with a temperature of 313, and my outer is colder with a temperature of 293. Set it up. Let's go. PRGH is inlet. My outlet, inner surface, and my outer surface. Okay, my inlet is fixed, which is equal to 1 bar. My outlet though is at a lower temperature, uniform 0. My inner surface is the same, outer surface is the same. Same for P. It takes the P hydrostatic pressure value to solve for the pressure values. So hence the name is calculated. Inlet, calculated internal field, which is also equal to 1 e power 5. Outlet is calculated there you go. This looks good. This is done. Now we move on to minus 9.81, 0. Since gravity is acting in the negative x direction, my momentum transport is laminar. Now we come to the thermophysical properties of the medium, the fluid medium. I solve based on density. My transport properties are constant. I'm specifying enthalpy related values. My equation of state is Boussinesq, which is a linear equation between density and temperature. And how I'm solving energy is through sensible internal energy. My rho is 1000, T naught 300, it's 3.3. My CP is 4185.5. Heat of formation is 0. My transport, that's right. My Prandtl number of water is close to 7. Prandtl number, which is equal to mu into Cp times divided by the thermal conductivity of water, which is 0.598, which gives a value close to 6.997. Looks good. The transport properties. Yeah. 1 e power minus 3 by 1000. This is again 3.33. 1000. Laminar Prandtl number is 7. Now we move to system. We remove the block mesh. We go to control directory, buoyantPimpleFoam. I start from my start time. So end time, which is 5 seconds. My delta t is 0.001. Might take a long time to solve it. And my write control is adjustable runtime. Should OpenFOAM adjust my time step? Yes, I shall give it the option. I shall give a condition, which is max current. The current number should not exceed 1. Say in a cell the current number exceeds 1. OpenFOAM shall automatically adjust the runtime lesser than this specified values or any value that was taken. My write interval is 0.2 seconds. Every 0.2 seconds it records it. I shall keep it to ASCII. True. I do not need this function. For my finite volume schemes, I shall remove the turbulence terms. Rest all are required. It looks like we are good to go. Now we shall solve it. To solve, type the name of the solver in the console and press enter. It looks like it's solving. It's automatically adjusting the time step, as you can see. It's adjusting, taking a delta t of 1.7 already, and the ongoing time. It's using most of the procedures here. Yeah. In the next episode, we shall see post-processing in ParaView. And that's it for today. See you guys.